So hello students, welcome to our laboratory session. So we are going to have theoretical as well as demo part of your experiment. So I am going to show demo about band gap determination of a semiconductor. So in your manual you have at page 36, you will be having this particular experiment. Going to have this band gap determination. For doing this experiment, first we must know what is band gap. So you all know semiconductors. So it will be having valence band and conduction band. So at normal temperature, that is 0 Kelvin, so it will be not conducting. So when it is intrinsic, we have to give some amount of temperature such that valence band electrons will be moving to the conduction band. So in order to find out band gap, we are going to have the following experiment. So the circuit for doing this experiment is given as follows. We are having a battery. Here the circuit you first understand, then I will show you in the demonstration what are all the required things. So here we have, in this circuit we have battery and it is connected in parallel with voltmeter. Then the positive of the voltmeter is connected to positive of the ammeter. Then it is connected to the negative of the diode, and the positive of the diode is connected to the negative of the voltmeter again, and the entire diode is immersed in the hot temperature bath because we are going to find out band gap. So we need to give some amount of temperature. So we are immersing it in the hot temperature bath. Then to note down the temperature, we are inserting a thermometer in that, and this beaker is heated with the heating coil which is connected here. So this is the circuit. So let us do the experiment. For that I will show what are the required things. So this is the experimental arrangement for the experiment what we are doing. So this is band gap determination. The entire kit is here. So as I showed you in the circuit, so we have the battery here. So in the circuit we can see what are all the required things. We need a battery, we need a voltmeter, we need an ammeter, we need a diode, beaker with heating coil, then we have the thermometer, isn't it? So I will show you the required things in this for this experiment. Here we have the entire kit. Here we have the terminals for voltmeter. These two are the terminals for voltmeter, and these two are the terminals for battery, and these two are the terminals for ammeter, and these two are the terminals for this heating coil. Okay, so this is the heating coil. We are going to heat it electrically. For that it needs power supply. So for that we are connecting these to the terminals. This is the two terminals which is used for heating it. Okay, so these are the required things. So here it is connected as follows. So these are the terminals of battery, that is positive and negative of the battery. It is connected to the voltmeter in parallel. So what is that? Positive is connected to positive, negative is connected to negative. And from the positive of this, it is connected to the ammeter. Okay. See here, positive of the voltmeter is connected to positive of the ammeter. Here, this one is the positive of the ammeter, positive of the voltmeter. It is connected to this wire. And finally, we have the negative connection internally connected, this part, isn't it? This part of the circuit here in this is internally connected, and you can see here it is mentioned. This is the diode. Okay, so now I will show what is the diode. So in this sleeve we have inserted a small diode. A small thing you can see, isn't it? This small thing is known as a diode. This diode is connected negative to the negative of the ammeter. See, like this. Negative black color is negative here, red color is positive. So black color is connected to the negative of the ammeter and positive is connected to the this, and hence the circuit is closed. Okay, so here the circuit is closed, isn't it? In the same way, we have closed the circuit by connecting everything. So we have connected battery, voltmeter, ammeter, and in between we have connected the diode. So diode is this one, the small one is diode. Here you can see one black color line. That black color line indicates the negative of the diode. Okay, so since we are going to put it inside the hot temperature bar, we are just inserting it into the sleeve such that it will not be directly heated. So this is just a protection for the diode. So we have inserted into a sleeve like this. And now we are going to switch on the battery. So we are going to start the experiment. To begin with, we are going to have this is at room temperature now. So it will not be very much conductive. So in order to increase the conduction and find out the band gap, we are in need to put it into the hot temperature bath. So now I am switching on the heater such that this is oil. Okay, so this is oil bath, that is oil taken. Here you can see that it is getting heated. So hence it heats the oil. Okay, so now I will be inserting the thermometer to see the temperature. So the heater is on. It will be slowly heating. So let it heat. In the meantime, I will say what it is. So I am going to fix the voltage as 0.1 volt. So by adjusting this knob, I will be having the input as 0.1 volt for this entire thing. So I am giving 0.1 volt. Okay. So 0.1 volt is given, and let us wait till it heats up to 80 degree. Okay. So I am going to heat up to this oil up to 80 degree. After heating that up to 80 degree, I am going to switch off this heater. Then I am going to insert this diode. So in the meantime, I will explain what you have to do with the tablet column. So here we have given power supply as 0.1 volt, isn't it? So that you have to note it here. So we can write it as 0.1 volt here. Then we are going to have a set of temperature for which we are going to find out the current. Okay. So we are going to heat up to 80 degree, right? So let us start taking the reading from 75 degree. So I will be writing it from 75 to 10 temperatures like 75, 74, 73, 72, 71, 70, 69, 68, 67, 66 and 65. So I am going to measure temperatures I am going to measure current for these following temperature. So I have written like this. Okay. So I will be writing. So I am going to note down the temperatures, respective current for these particular temperatures. Okay. So I am going to heat it up to 80 degree. From 75 onwards, I am going to take the readings. So now I am waiting till it is getting heated. Now what you have to do is, you have to convert it into Kelvin. Then that Kelvin has to be converted. You have to take the inverse of that Kelvin and you have to note it here. Okay, after doing all these things, you have to note down the current here. Now, so finally this current in the ammeter is not varying because it is at room temperature. But after putting it, let us see what happens to the reading in this ammeter. Okay. So let us wait. So you can see the temperature is slowly. You can see I have heated up to 80 degree. I will wait till it reaches 75. Then I will start taking the readings. So for this particular decrease of temperature, for each degree decrease of temperature, we are going to note down the ammeter current. Before that, I am going to put this diode inside the hot temperature bath. See now the reading is in some 2.0, isn't it? So as I introduce this diode inside the hot temperature bar, you can see the reading drastically changes. Yes, can you note down? Yeah. Now we are now we can say that because of the temperature given, the electrons from the valence band, it's getting raised to the conduction band, crossing the energy barrier. So how much it crosses, that we are going to measure using reverse saturation current. For that only we are going to measure this amount of current here. So for each degree fall of temperature, we are going to measure what is the reading in this ammeter, what is the amount of current is present in this ammeter. Okay, so now the thermometer has decreased to 78 degrees, so I will start taking the reading from 75. So let us wait for a while. So in the meantime, we have noted, already we have noted down some 10 temperatures. So this 10 temperature I have noted down. For this I have converted into Kelvin, and then I have taken the inverse, Kelvin inverse. For this particular value I have taken inverse, that is 1 by K. For that I have noted down the readings. Now from 75 degree I am going to note down what is the current in the ammeter. So I am going to note down that reading here. Follow? Okay. So this is how you have to plot the values. You have to record the data what you observe now. So for each degree fall of temperature, I am going to note down what is the current, because using the technique of reverse saturation current, we are going to find out what is the band gap of the semiconductor. So shall we do? Yes. And now it has been decreased to 75. So for 75 the reading is 42.7. For 74 the reading is 38.5. Then for 73, the reading is 36.9. So likewise, we will be noting down temperature for current for each degree fall of temperature. Okay. For 72, 35.2. For 71, it is 33.8. You can see that the current is varying. So as the temperature decreases, the current also decreases, you can see. So using this, we are going to find out what is the band gap of the given semiconductor. So now the semiconductor is inside the hot temperature bar. For 70, the reading is 31.9. For 69, 30.8. For 68, the reading is 29.6. For 67, 28.4. For 66, 27.5. For 65, it is 25.8. So we have finished taking the readings, that's all. So we have noted down temperature versus current reading. Now using the reverse saturation current, we are going to find out the band gap using the readings. So these are the readings noted down from the following experiment. So for these 10 readings, that is for each degree fall of temperature, we have noted down what is the current in the ammeter. So now we are going to find out, using this graph, we are going to find out what is the band gap energy. So we have to plot a graph. So how you will be plotting the graph for this particular value? You will be taking log. Okay. After taking the log, you will be getting a value like this. Okay, so all the values will be in negative. So you will be getting a value like this. When you take log, you have to take this particular value into 10 to the power of minus 6 because it is a microammeter. So the measurement of current is in microamps. So when we take log, you have to take log along with this 10 to the power of minus 6. So as a result of that, we will be getting a set of readings which is all negative. So we have to plot a graph. We have to plot a graph like this, because 1 by t is all negative, right? So we are plotting along the negative y-axis because log is is taken along y-axis. 1 by t, this value is taken along x-axis. Since all these are negative, we are plotting it along negative y-axis. Okay, so we have to plot this 1 by t versus log is. Follow? So the graph you obtain will be like this. I'll show you. So the graph you obtain will be like this, and for this graph you have to find out slope. Okay, after finding slope, you will be substituting in the formula given. So this is the formula. While substituting, we will be getting the values. I will show it here. So this is the formula for this experiment for finding band gap. Here all the values given are constants, and only thing what you are going to find out is your slope. From the graph which I showed you previously, you can find out slope, and that value will be substituted here, and when we finish the calculation, we will be obtaining the energy gap, that is known as band gap energy determination. Is it clear? Thank you all.